This video is on a rule called L'Hopital's rule, not L'Hospital. Notice that there's no S hanging in here. It's not a hospital, it's L'Hopital. And L'Hopital's rule is a tool for limits, specifically limits that we'll talk about in a second. But whenever you see limits come up in problems, you should probably either think your first thought should actually be L'Hopital's rule, because often that's the tool that we're going to use to evaluate them. And L'Hopital's rule says something very, very cool. It says that if you have the limit as x approaches some number, c, and this could also be positive or negative infinity, of a quotient. So if you have, not f of c, sorry, if you have f of x divided by g of x, that under certain conditions, and here are the certain conditions. So let's say that you plug in c, or you plug in positive or negative infinity to f and g, and you get one of the following what are called indeterminate forms. Indeterminate forms. And if you get the forms that are 0 over 0, or infinity over infinity, and this could be plus or minus, what you can do is you can use L'Hopital's rule, and I like to put like an LHR on top of my equal sign to explain that I'm using L'Hopital's rule. But what we do is we continue doing a limit, but we change the original problem, and the original problem changes like this. Instead of doing f over g, we simply do f prime of x divided by g prime of x. And again, this only works with the following indeterminate form, 0 over 0, plus or minus infinity over plus or minus infinity. But essentially what we do is, if this limit doesn't work out, we take the derivative of the top, we take the derivative of the bottom, and see if that works out. And guess what? If that might not work out, and it matches one of these forms, you can keep going until you get an answer that you like. So let's go ahead and look at some examples of this. The first example is we're going to look at the Bobo Botan eats DC example. And specifically, we're going to look at Bobo and eats DC, because Botan is pretty self-explanatory. I guess we could look at all of them. Why not? So let's say that we're doing a Bobo, and we have the limit as x approaches positive infinity. We want something bigger on bottom, so let's just say we have 2x divided by like x squared plus 7. Well, if I plug in infinity, essentially the top is going to go to infinity and the bottom will go to infinity. This gives me the indeterminate form infinity divided by infinity. Therefore, I can invoke L'Hopital's rule. So I'm going to write LHR for L'Hopital's rule, and then I'm going to write the limit as x approaches infinity. And now check this out. All I do is I take the derivative of the top, so 2, and divided by the derivative of the bottom, which is 2x. Okay, and now I evaluate the limit. Notice that the 2's will cancel, I'll end up with a 1 on top. But now I have the limit of 1 over x as x goes to infinity. And this is very clearly 0 because there's no x's on top anymore. And so this is a cool application of L'Hopital's rule, because now we can see that actually what's happening is that the powers, when we take the derivative, this exponent wins, because when you take the derivative, it stays there, whereas the x on top went away. The Botan works very similarly, except the top wins, and so because the top wins, that's going to shoot it off to positive or negative infinity. So let's look at the eats DC example. So let's say that we have the limit as x approaches infinity of 3x squared plus 2x plus 7 divided by x squared minus 18x minus 49. I just made up numbers. They look snazzy. Let's check to see that we can, in fact, use L'Hopital's rule. If I plug in infinity into this, this is going to infinity, this is going to infinity, so in fact the top will go to positive infinity. If I plug in infinity into the bottom, this will go to infinity, and this will go to negative infinity, but really the x squared is bigger than x, and so this will also go to infinity. So I do have the indeterminate form, infinity over infinity. I invoke L'Hopital's rule, and now I'm going to write the limit as x approaches infinity. And now I just take the derivative of the top, which is going to be 6x plus 2, divided by the derivative of the bottom, which is 2x minus 18. Now, when I plug infinity into both of these, notice that the top still goes to infinity and the bottom still goes to infinity. I have the indeterminate form infinity over infinity, so I invoke L'Hopital's rule again. And so now I have the limit as x approaches infinity of taking the derivative again. I get 6 over 2, which now doesn't have any x's in it, so I can drop the limit, and 6 divided by 2 gives us 3. And 3 is the answer that we expected by dividing the coefficients from the Eats DC. So really, the bubble-bottom Eats DC is L'Hopital's rule, but only one application of L'Hopital's rule, because L'Hopital's rule can also work for exponential functions and that sort of thing. So hopefully this gives you a better sense of why Eats DC works. Let's look at some other examples involving different types of functions. So here we have the limit as x approaches 0 of e to the 2x minus 1 all divided by x. If I plug in 0, let's do a quick check, I get e to the 0, which is 1, and 1 minus 1 is 0. And if I plug in 0 to the bottom, I get 0. We have the indeterminate form 0 over 0. Therefore, I'm going to use L'Hopital's rule, because L'Hopital's rule works for infinity over infinity and 0 over 0. And now I'm going to rewrite this as the limit as x approaches 0 of the derivative of the top. And so the derivative of the top is going to be e to the stuff, chain rule 2, the negative 1 goes away, and the derivative of the bottom is 1. Now I need to check by plugging in 0. So if I plug in 0, I get e to the 0, which is 1. 1 times 2 is 1. And then I have a 1 on... No, what am I doing? 1 times 2 is actually 2, students, in case you didn't know that. So 1 times 2 is 2, divided by 1. This is not an indeterminate form, and so the answer is, in fact, 2. So L'Hopital's rule does give us a lot more power, and it's really easy to do this, but it gives us a lot more power in evaluating funky-looking limits like this. Just as a very quick note, when you're doing these derivatives, you are not doing the quotient rule. You're doing like the wrong version of the quotient rule, which is just like take the derivative of the top, take the derivative of the bottom, and divide them. In this case, that's correct. You want to do that for L'Hopital's rule. Now, there are other indeterminate forms for which L'Hopital's rule will not work. For example, you could have the indeterminate form 0 times infinity. So an example of this would be the limit as x approaches infinity of e to the negative x times the square root of x. So very clearly, if I plug in infinity into e to the negative x, that's e to the negative infinity, which will go to 0. And if I plug in infinity into the square root of x, the square root of infinity will blow up to infinity. I'm confirming that I have 0 times infinity as my indeterminate form. Now, to use L'Hopital's rule, I must have 0 over 0 or infinity over infinity. And so if you get 0 times infinity, oftentimes it's a very, very simple way, there is a simple way of rewriting this to make it match one of the above forms. And almost all the time, that involves just dropping one thing into the denominator. And so I would have the square root of x divided by, if I dropped e to the negative x down, I get e to the positive x. Now let's check by plugging in infinity. If I plug in infinity, the top goes to infinity. Oh, and now the bottom also goes to infinity. Therefore, because I have the indeterminate form infinity over infinity, now I can do L'Hopital's rule and go from there. So that's a strategy for doing that. There are also some very, very strange indeterminate forms, and those are things like 1 to the infinity, which does not always equal 1, contrary to popular belief, or 0 to the 0, which also, who knows what that equals. The word indeterminate comes from the fact that you cannot determine the answer. And so, just like if you have things that are 0 over 0, these could equal basically any number. It's not undefined, because undefined means that you can't find a number, is that really you could set up a problem where you get 0 over 0, but just like a whole, that could be any number. Alright, coming back to these two indeterminate forms, let's look at an example, and this will be a little bit long, so stay with me. We're going to look at the example of x approaching 0 from the plus side of sine of x, wait for it, to the x. So this is kind of a weird thing to do. And, you know, just to confirm, yeah, we have 0 to the 0 because sine of 0 is 0 and x approaching 0 is 0. So in order to do this, just like we did with derivatives, where we had a function of x to a function of x, we're going to use the idea of logarithmic separation. And so what we do is we start out by saying, let's let y equal all of this stuff. And then what we're going to do is we're going to take the natural log of both sides. So we're going to do the natural log of the limit as x approaches 0 from the right of sine of x to the x, and this is going to equal the natural log of y. And now the reason I do this is because now I can bring down this x in front of the natural log. So let's do that now. We're going to get x times the limit, and actually I can pull the limit out too. So if I write this, what we really have is we have the limit as x approaches 0 from the right of bringing down that x times ln of sine of x, and this is going to equal the ln, the natural log of y. Does this help us? Well, let's find out. Now x is still approaching 0, so let's check. Over here, this would approach 0, that's fine. And then over here, sine of 0 is 0, and then as x approaches 0 from the right, natural log of 0 from the right, this goes to negative infinity. Uh-oh. So what I have basically is I have 0 times negative infinity, but using the strategies from, wait, there it is, last time, I want to drop one of these terms into the bottom. So the way I do that is I take this x and I'm going to drop it into the bottom by doing a 1 over x. Okay, and you'll see why this works in a second. So let's go to the next page. So right now we have ln of y equals the limit as x approaches 0 from the right, and I have that natural log of sine of x on top divided by the 1 over x in the bottom that I just dropped down. So let's check again to make sure this works. If I plug in 0 into the top, I'm going to get negative infinity. And now if I plug 0 into the bottom, 1 divided by 0 is undefined, which means plus or minus infinity. So I do, in fact, get this infinity over infinity thing. Whew. Great. Now I can use L'Hopital's rule. So all of this was a setup to get to L'Hopital's rule. So we're going to do the limit as x approaches 0 from the right, taking the derivative of natural log of sine. The derivative of natural log of stuff is 1 over stuff, and then chain rule, cosine. And then the bottom, the derivative of 1 over x is negative 1 over x squared, like that. Let's clean this up by simplifying. I still have the limit as x approaches 0 from the plus side. Cosine divided by sine is cotangent x, and then on the bottom I still have this negative 1 over x squared, and because cotangent is really 1 over tangent and this is negative 1 over x squared, I'm just going to flip this fraction. So we're going to get limit x approaches 0 from the right of, the top is going to become negative x squared, so the top becomes negative x squared, and then the bottom, because I have 1 over cotangent, that would drop a tangent of x to the bottom like this. Alright, let me rewrite this so it's a little bit clearer to see. We'll have limit x approaches 0 from the plus side, negative x squared divided by tangent of x. Alright, now we're going to plug in 0. So I plug in 0 on the top, I get 0, and I plug in 0 into tangent, I also get 0. So guess what? We have the indeterminate form 0 over 0. I get to use L'Hopital's rule again. So using L'Hopital's rule again, we take the derivative of the top and the derivative of the bottom. And the derivative of the top will become negative 2x, and the derivative of the bottom, the derivative of tangent, is secant squared. So now I can plug in 0 again, and when I plug in 0 into the top, I'm going to get 0. And then secant squared is 1 over cosine squared. Finally, if I plug in 0 into cosine, I get 1. So eventually this ends up being 0 over 1, which is simply 0. This is a very good thing. So our limit ends up being 0, but we are not done yet, because just like with logarithmic differentiation, I started off with natural log of y equals 0, therefore y equals 1, and y was the original limit that we were wanting. So our final answer is that this equals 1. Hooray! Again, just want to point out that this is kind of weird because we started with something that was in the form of 0 to the 0, and we got something that was nowhere related to that. Because you've learned the rule that something to the 0 is always 1, but 0 to the anything is always 0. And so, really, so 0 to the 0 is indeterminate and really could be anything, and in this case, the specific problem gave us 1 as our answer.